Okay, let's start today. So in the last week we were looking at the issues with fully differential op-amp and especially common mode feedback, right? Again, to summarize that, so this is the simplest fully differential op-amp, and here the issue is, if you actually look at this circuit for DC bias or for common mode signals. Why don't you come here? Just so if you look at the scenario for DC bias or for common mode signals, you have this as the equivalent circuit, right? And here, as we noticed, we had two current sources biased independently, and that's what was making this node voltage to be not defined. So this required a separate feedback mechanism for setting that, and this is the basic idea. You basically sense the common mode average of the two voltages, compare it to a particular reference, and you can keep, let us say, the bottom current source fixed and tune the top current source, or vice versa. Okay, so I just wanted to highlight one more property of, or one more feature of common mode feedback, and for that let's actually look at the common mode half circuit for this. So I'll basically what do I do? I'll change it here itself. So, or maybe I'll redraw it. It's okay. Let's see. So if I redraw this, I'll have basically the top side PMOS. Of course, we have two times of the transistor. I'm not showing that explicitly, right? And actually, for simplicity, let's assume we take a pseudo differential case like this. Okay, fine. So the common mode half circuit is going to look like this, and then you have the rest of the guys. So basically, I'll redraw the same thing like this. Okay. Fine. This is a common mode half circuit. So I'll just erase this now. Great. So again, this is connected to some voltage. Okay. So let us say some VB. So now let us say I actually make some more space. Sorry, hold on. I'll draw it like this. Okay, let us say now we make an experiment. So let us say at the output, here I go and inject a current, a step current. Okay. And remember that we'll have parasitic capacitors everywhere, here, etc. Okay. So let us say inject the step current, and for simplicity, let's say the CMFB is not there, right? This was a normal setup. I'm trying to inject a step current at the output. So let's assume the R0 for transistors are all infinity. What will happen to the output? So how will the output look like? Yeah, charging. How will it charge? Linearly. I just have a capacitor. The current source gets, the current gets pushed into the capacitor. So you basically have, and what is the slope of the ramp? Let us say the current is I. What is the slope of the ramp? I by C. Okay, great. Now let us say if this guy, I mean if you consider the finite output resistance also, what will happen? Will it keep ramping up, or what will happen? So recollect, now you have a scenario like this: small signal current I, you have the capacitor and the output resistor. So what will happen? It will exponentially charge and settle like this, right? Basically not like this. Maybe I'll just show with a different color, right? And here also, what can you say about the initial slope? It will be same. Initially it will start to ramp up, but then the rate of slope of the ramp will reduce, and that's what gives you the exponential settling, right? So now let us say I keep reducing this capacitance here, or let us say, let's not do that. Okay. So now let us say now go and connect the feedback here. Okay. Now the common mode feedback is present. Once again I apply the step current. Initially, of course, the voltage will try to ramp up like this, but after that, what do you think will happen? In steady state, what do you think will happen to the output voltage? It will be VCM ref. So incrementally there is no change. Again, this is assuming that this guy has infinite DC gain, right? Let's assume that. So this loop will set the common mode here to VCM ref. So incrementally there is going to be no change. So initially you will have something like this, and then it will do this. Something like this, and set array. Okay. And the speed with which this settles to the final zero increment, what does it depend on? The omega u of this feedback loop will determine how fast this response is going to happen. Fine. And of course, now depending on the things, it can do faster, slower, lot of things. Great. So this is something you know. So now let us say I want to, let me erase all this, and again I want to highlight that the initial slope here, what is that? It will still be I by C. That at t equal to 0 plus, if I look at the slope, that is still I by C. Okay, great. So now this is the scenario we have. Now let us say I want to model the output, right? So look at the experiment. I applied a step here. And if I apply the voltage here, it looks something like this, some kind of ringing, and then it settles eventually. So if I were to model the output side using a simpler equivalent circuit, what do you think that equivalent model will contain? I apply a step current. I find that the voltage kind of rings and then damps eventually. So if I were to model this using simple circuit elements, what all do you think that model will contain? See, the thing is right, I have applied the step current, right? And I know that if I observe the voltage here, it has some kind of ringing like this. So what might be the simplest elements you can put here to emulate the same behavior? Second order system, yeah, okay. So what elements? If you have only RC, do you think that will happen? Yeah, I mean, definitely there should be LC because there is some sinusoidal ringing. So you will have an equivalent LNC. Let me actually. Fine. But if I just have an LC, that okay. It will. I mean, do you think? I mean, it will settle to what value here? So incrementally. Oh, sorry. I mean, let's say this is VCM ref, right? I mean, fine. Okay. Yeah. If I just have LC, if I apply a step current, what will happen to the output? It will continuously ring. But here I see that it kind of dies to 0. So what other thing I should add here? Where do you think I will add the resistor? I mean, I can add a resistor in series with the capacitor, inductor. Or first of all, yeah, do you think I can add the, do you think the damping can be emulated by putting a resistor here? But do you think that models this circuit? In steady state, what can you say about the voltage, incremental voltage? In this circuit, in steady state, what is the incremental output voltage? 0. So here, in steady state, what will be the voltage? Huh? Steady state, capacitor is open, inductor is short, all the current flows here, it's I times R. So do you think the resistor should come here? That cannot come because that doesn't model a circuit. So the resistor will come in parallel to this like this. Right? Is that okay? This is the equivalent circuit, at least qualitatively it should make sense. Fine. Of course, this capacitor should not be surprising because you already have this capacitor, that's what is coming here. Right. Now let's try to qualitatively understand what is giving rise to this inductor and resistor. If you put a, okay, he is saying you put this, if I put a resistor in series with the current source, what happens? What if this is current I, what is this current? So do you think the resistor plays any role? I mean, a resistor in parallel with an ideal voltage source or a resistor in series with an ideal current source, they are irrelevant. Okay, so if you have a common mode feedback loop, what is the loop trying to do?
Setting the
output common mode voltage, it wants to set to some reference voltage Vref, right? So even if I go and apply a step jump here, the negative feedback loop's job is to go and make sure that this voltage is brought down to VCM ref, right? So here if I just draw the incremental output, it was already at VCM, I'm saying how much is the change. Initially it will change, but then the loop will kick in and make it go to 0. Is that okay?
But it was VCM ref.
Yeah, VCM ref, see, that is, let us say, the DC bias. I apply a small step. Here I'm plotting only the incremental output VU. Fine? If I look at the total output, this 0 will not be 0, this will be VCM ref, right? That's all. Okay. So is this okay? I mean, if you have to model this, you will have parallel RLC. Of course, this capacitor should not be surprising because you already have it. If it's surprising, I mean, it's okay, it can be surprised, it's okay. Right. So let's understand why this inductor is coming. And for that, let me actually take the circuit again. Or actually, we'll copy this. Oops. Yeah. So, let us say I apply the step current here. Initially, what is the slope of the voltage? I by C. Now I know that this capacitor is what is giving rise to the capacitor. So if I remove it, I should still see this effect of inductance. Okay. So now which means that if I make this capacitance go to 0, I should see a purely, not purely, some kind of inductive behavior in the output resistance. And for making this capacitor go to 0, I will do the following experiment. So I know that if the capacitor is there, if I apply a step current, the slope of the output voltage at t equal to 0 plus is I by C. Now if I keep reducing the capacitance, what do you think will happen to the output slope? It will keep increasing. So if I remove the capacitor in 0, what can you say about, basically I'll say a step current. So if the capacitance is 0, what can you say about slope at t equal to 0 plus? Goes to infinity. So do you know some element for which if you apply a step current, the change in the output at 0 plus goes to infinity? Inductor, because inductor is what? Inductor voltage is? Right? So if the current is a step, at t equal to 0 plus, the slope basically blows up. Right? And that's what is actually giving rise to the inductive behavior. Okay. And I mean, this is a typical feature of any negative feedback loop that is actually trying to realize a voltage controlled voltage source. Okay. So here if you see this feedback loop, it is trying to make sure that this common mode voltage here is exactly equal to VCM ref. Right? That's what its job is. So in a way it is trying to make a voltage controlled voltage source where the output voltage is dependent on VCM ref. Okay. So if we have a negative feedback loop like this, let me actually make some more space. So basically what we have is this, I'll read out slightly, VCM ref, that is basically compared to the output, and then we have something, right? Basically what I'm saying is this guy along with this forms a two-stage OTA, you know that, right? And actually something I missed here, so hold on. Okay, so here in the circuit common mode feedback, remember we also have to compensate it, right? And remember compensation we did using Miller capacitor like this, right? So that I'll also include that. So basically you'll have the capacitor like this. Okay. You have a resistor here, I missed it, I'm really sorry. Something like this. Right? The resistor is not relevant, so I'll not show, it's okay. Fine. This is okay. I mean just the compensation capacitor is there. Fine. And this guy is the first stage, this is the second stage. Together I can call it to be an OTA. And for this two-stage OTA, one input is this, other input is this. So this is what we have. Okay. So here, right, This again trying to form a VCVS kind of system. Here also, if you actually go and find the output resistance, you will still see an inductive component, and that simply happens because if you apply a step current at the output, right? Again, if there is no capacitor here, if you remove the capacitance part, the step current will result in infinite slope for the voltage at 0 plus, and that will again give rise to the inductive behavior. And that is actually happening because, see, if I say if the negative feedback loop is infinitely fast, then can you say how this output voltage will look like? It will incrementally, there will be no change. Because the negative feedback loop is infinitely fast, even though I am applying a step current, it makes sure that the steady state is reached instantly, right? So the inductive behavior is not coming because we have this negative feedback loop. It is because of what in the negative feedback loop? Delay in the negative feedback loop. If this was instantaneously fast, it's always 0. Then you will not have anything. It is because you have a delay in the negative feedback loop. That's what is actually giving rise to this inductive component. Okay. And I mean here also, right, let us say this has no delay, so let us say there are no capacitors inside the OTA. If let us say this has an effective GM of GM, what is the output resistance here? 1 by GM. And if I say the feedback loop is infinitely fast, what can you say about the value of GM? It's also infinity. So 1 by GM tends to 0. So that's what, right? It's now behaves like a very good voltage source. So the output resistance here is 0. But of course, in practice, you can't have infinite GM, and the GM will also have its own delay. And that finite speed of this negative feedback loop is what is emulating this inductive component. So any VCVS kind of negative feedback loop we have, you find the output resistance, you will have an inductive component. Okay. And I mean here also, right, see here I know that if this has no capacitor, it is just GM. Output resistance is what is 1 by GM. So let us say this has poles inside this, so let us say it is some GM of S. Now if I find the output resistance Z out of S, what will that be? Huh? I mean, if it was just a purely, I mean, no delay inside the GM, so it was just GM, the output resistance was 1 by GM. If let us say it has poles inside this, so it is not a constant GM, it is GM of S. If I find the output impedance versus frequency, what will that be? 1 by GM of S. That's all, right? It's the same thing. Okay, and of course now GM, as we told, has some poles, so you can think of it as GM by some, let us say 1 plus S by P. So if I simplify this, I'll have something like this, right? So this is giving rise to the inductive component, because if you have S times something, that is the impedance of an inductor.
This circuit, can you repeat how you draw?
Okay. This is basically what I'm doing is, this is okay, right? So here I'm considering this as my first stage OTA. I mean, remember that if I break the loop here, this is like, I mean, I'll not break the loop, hold on, let me do it properly. If I break the loop here, this is like first stage of, this is like a first stage OTA. Output goes to a second stage OTA, which is compensated, and the final output is connected back, right? So this entire thing is a two-stage OTA, which I have modeled like this, right? And that's what is put in unity feedback. Huh?
So in previous case, when we took capacitor is 0, then we took the inductor here.
Correct.
So, but that output node will be attached to CL.
Correct. That's what. In addition to the CL, you will have inductance, right? I mean, CL is, I mean, the capacitance here is coming because you will have a load capacitor or some parasitic capacitor here.
But that will be very high, so how can we simplify this?
That is okay. It can be, what I'm saying is, if you were to model the total impedance, you know that the capacitor is going to come. That is included. In addition to that, what all we have. So, which means you first ignore the capacitor and see what is the rest.
Okay. But the characteristic you modeled it using an inductor.
Correct.
We model it using a second order underdamp using capacitor. RC only.
It's a model, right? You can do anything, but this is the simplest model, right? If you have a second order RC, it might not be easy to do it, right? But this is more straightforward. But the point is, you will have, see, even if you do it second order RC, you will find that you will have an inductive behavior somehow, because if you put it like this, you will find that the output resistance increases with frequency at some point, and the simplest is inductor. So this basically captures the effect of inductance. So let's just look at the resistor. So what do you think is giving rise to the resistance in the CMFB? I'll erase this. So inductor part is fine, right? So the VCVS kind of negative feedback loop in presence of a delay that emulates an inductor in some range of frequencies. That's all, right? Yeah. So now, what do you think is giving rise to the resistance here in the circuit? Again, the simplest way to see is, if I remove the resistor here, let us say the resistor is not there, right? How will the response look like here? It will kind of oscillate like this, basically something like this. So here, if I remove which of the components do you think the system will oscillate? This is basically CL, this is CP, this is RCCL. If I remove which of the elements here, do you think the output will oscillate or it will be less stable? No, huh? Sorry? Why? Right? See, if let us say this CCM is not there, it is a two-stage OTA put a negative feedback loop. What can you say about the system? It may not be well compensated, and in fact, if you assume the output resistance are all infinity, what can you say about the pole locations? No, if the output pole will be at origin, output resistance is all infinity. Remember, pole is some 1 by RC. I am saying R is tending to infinity. So you have two poles, both poles will be at origin. So it is as though you have two integrators like this, two-stage OTA, and you are putting it in negative feedback. What will happen to the closed loop? It will, if you find it, it's going to be S square plus something, right? So let's say it's omega something. It will be some S square plus omega hat square. It will nicely oscillate, right? But what is bringing the, what is making this system, what is making the system stable finally? I mean, what do we do to the system to make it stable? You add the Miller cap here. So that is what is bringing the stability. So it should make sense that the resistive component, which is responsible for damping the oscillations, should be coming mainly because of this guy, right? And it's also easy to see actually if you find the output resistance. So I'll basically redraw the same thing. This is, let us say, CP, CCM, and I mean I've already taken into account CL, so I'll not worry about it. This is CL. If you find the output resistance here, see here, let us say the output voltage changes here. Initially, if CCM was not there, let me do it this way, right? I'll read out the same thing and explain clearly. So we are injecting a current here, test current. So before applying this current, the negative feedback loop was stable. So the two currents here were equal. Now I am adding an extra current here. So which means the total current that is getting pushed into this node is greater than the current that is getting pulled out. So to make it fine, what should happen to the current in the transistor? It should decrease. And for that to happen, what should happen to the gate voltage? Increase. So the feedback loop should somehow go and increase the voltage, right? And as we saw, if you inject a test current, this voltage increases initially, and the feedback loop should basically finally increases voltage. Now, if you have a connection like this, you'll have a delay in this, delay in this. There will be a lot of delay in the loop, and that's why you'll have oscillation. Now if you go and put the compensation capacitance here, if this voltage increases, you don't have to wait for this path to respond. So you'll have a conduction through this capacitive thing, so that will make sure that the voltage here also increases quickly, and that's what is kind of making the system stable, right? So, and in fact, if you find the resistance here, if let us say this is some V test, what can you say about this voltage? V test times, it's a capacitive division, whatever, CCM by Cp plus CCM. So what will be the incremental current? The gate voltage is this, Gm times that voltage. So that is the incremental current, real part of the current. So the resistance is what? I am applying a test voltage, Vt. I find that this draws a real current here, which is this one. So what is the resistance? Yeah, it is basically what? Yeah, it's basically 1 by Gm times that ratio, whatever. Something you forgot. Okay. So that is, I mean, if you were to model your common mode feedback loop, we can model it like this using a series, parallel RLC, where the capacitor is of course coming from the total capacitance at that node. The inductance is coming because you are having a negative feedback loop trying to form a VCVS, and there is an inherent delay in the loop. And the damping portion is coming because you have made something to make sure that the loop is stable. So whatever you are adding to stabilize the loop will contribute to this damping resistor. Right? So, and in fact, right, so as we saw, this will have an inductive thing. What is the simplest voltage controlled voltage source you know? I mean, it's not even op-amp, simplest common? It's not, common source is this. Common drain, right? Source follower, right? So if you were to actually, let us say this is RL. So here if you consider the capacitances here and find the output resistance, you will find that this will also have some kind of an inductive behavior. And in fact, in your first, in the mid semester, you also had a question. What was the effective impedance looking like? Inductive. Okay. Of course, this was what I initially thought to give, but then I changed it to make it simpler. But anyways, so this is a typical property of feedback.
Inductor is coming in model because when we apply step current.
Correct. I mean, if you want to find the impedance, what do? Impedance is V by I, right? So you have to apply a current and see what is the voltage. So that's what you do, right? So great. So that's what I wanted to cover. So I think now we'll probably look at some problems. I'll not record this.